All right, hello Math 30-1 students. We are in lesson 2 today, so let's just maybe see what I can do here. Ooh, let's have some fun. Lesson 2. All right, in the previous lesson, we learned all about H and K. So if we go back to the cover of our notebook here, you will notice that we are working on this transformation of functions equation. And we've established what H does and what K does. H moves us left and right. I remind you that it is backwards. X minus 3, right. X plus 4, left. All right? K moves us up and down. K makes perfect sense. All right. The only thing we have to worry about with K is whether or not they accidentally write, well, I shouldn't say accidentally, on purpose to screw with you, write it on the left side of the equation. Always make sure that you have y equals. So what we have to realize thus is that H influences X and K influences Y. All right, we have a fairly short lesson today, which is fine. I believe that I'm on page 7, I think. Are we on page 7? We are on page 7. So today we are going to learn about reflections. Now, reflections simply turn things around or upside down. If you were facing right, maybe I'll reflect you so that now you face left. If you were facing up, now I'm going to reflect you to face down. All right? So, on the grid provided, plot the point 2, 5. Okay, 2, 5, I believe is right about there somewhere, more or less. Use the x-axis as a mirror line. Now, what do they mean by that? Well, what they're saying is, here's the x-axis, and we are going to reflect over it. All right? Use the x-axis as a mirror line, or a line of reflection, and plot A prime. So where is A prime going to end up? Well, what this means is, when you flip over the x-axis, this 2, 5 becomes 2, -5. All right? Notice that when we flip over the x-axis, it influences y. So what are the change coordinates to A? Well, lo and behold, I think this is now 2, -5. All right? Boom. Reflect the point A in the y-axis. Oh, okay, fair enough. So now they want us to reflect in the y-axis. Well, no problem. So I take this 2, 5, I flip it over the y-axis. Won't it become -2, 5? So here we get -2, 5. Boom. So what does this mean? When you reflect in the x-axis, you change y's. When you reflect in the y-axis, you change x. All right? So, hey, maybe I've just answered some of these questions. When a reflection occurs in the y-axis, it is the x coordinate that changes signs. So therefore, we can say, oh, whatever x was, put a negative on it. All right? What that means is, if you were a positive x, you'll become a negative x. If you were a negative x, won't a negative become positive? So this is the notation f of -x. That results in a reflection in the y-axis. When a reflection occurs in the x-axis, it is the y-coordinate that changes signs. And we use the notation f of x becomes -f of x. So, this is saying put the negative on the whole function. This is saying put the negative only on the x portion of the function. Thus, change your x, change your y. That's what that means. All right. Given the graph of the function below, draw the graph of negative f of x. Not a problem. Okay. Negative f of x, right here, the y changes. So this point here, who is negative 3, 2, becomes negative 3, negative 2. This point at 0, 6 becomes 0, negative 6. This point here at 1, 0, well, put a negative on a 0. What happens when you put a negative on a 0? Not much. Therefore, it stays right there. We're going to talk about this concept in a second. 2, negative 3 becomes 2, positive 3. 4, 4 becomes 4, negative 4. So I have turned this function upside down. That's what happens. Oops, right about there. That's what happens when you have a negative f of x. You flip over the x-axis. Now, it then says, describe the location of invariant points. Now, invariant points are points that don't move. Now, I want you to think about this. I realize you can't see me, but I often give this example where I take my daughter and I grab her by the waist and I turn her upside down. So, because she's still young, I can physically do that. There will come a point where she'll be too big for me. But do you agree that her feet will move up to where her head was, and her head will move down to where her feet were? All right? What doesn't move? Her waist. And the definition of an invariant point is going to be a point that doesn't change after transformation. Well, this first point certainly changed. This second point certainly changed. Right here, I believe that this was 1, 0. What did it become afterwards? It became 1, 0 is the invariant point. Now, take a peek at this. This point down here certainly moved up there. This point here moved down here. And I apologize for drawing this line poorly. I think I should actually try and fix that. Let's see if I can do a little bit better job. Maybe I can erase some of this here. And I'm going to see if I can do a better job by possibly doing this. Bada bing, bada boom. There, I've done a better job. What did I make sure I did? Notice this other point right about there. Now, unfortunately, I don't know what it is. They haven't given me a specific point location, so I couldn't tell you exactly what it is. But it is going to be, I'm going to guess, let's just take a peek. Oh, about 2.9, give or take. I'll just put that line back. So I'm afraid I don't know what it actually was, but I'm just going to say it was about 2.9, give or take, 0. Now, I want you to notice, where are the invariant points when you flip over the x-axis? The x-intercepts. How come? Positive y's become negative y's. Negative y's become positive y's. What y's don't change when you put a negative on them? 0. Thus, when you reflect over the x-axis, your invariant points are always the x-intercepts. The diploma, I'm just going to erase this right now and then just tell you a diploma question. All right. One question that the diploma loves to ask, and you won't understand everything yet, but they'll say, how many invariant points are there when we do this reflection? And they won't ask you what they are. They'll expect you to say, oh, there's one right here, and there's one right there. The answer is 2 invariant points. They love that as a numerical response question. All right, oops, let's put that back, my bad. All right, thus, reflect over the x-axis, x-intercepts are invariant. How come? When you reflect over the x-axis, y's change. But wait a second, how do you change a 0 by putting a negative on it? You don't. It stays as 0. All right, page 8. What do we got here? Graph the function x squared minus 4. All right, no problem. To me, that is a nice little, let's see if I can make this thinner maybe. Is there a way to make this thinner? Yeah, maybe I can do this. Okay, here we go. All right, this is a quadratic who has a y-intercept of negative 4. All right, when I look for the x-intercepts, well, I put a 0 in for y, move the 4 over, and I square root, and I'll get my x-intercepts at 2 and negative 2. All right. Now, let's see if I could possibly make this a little bit better. When I put a 1 in here, 1 squared is 1 minus 4 is negative 3. So therefore, this thing's going to look here. This guy's going to go here. Oh, that was terrible, Mr. Chandler. Let's see if we can fix that. Oh, my goodness. Like I said, I'm doing this at home with my mouse. That's better. Let's put in a 3. 3 squared is 9 minus 4 is 5. So therefore, this thing is up here at 5, and this thing is over here at 5. Okay, there we are. So, can I attempt to connect these dots using my mouse? Oh, looks something like that. All right, gorgeous it is not, but you get the point. There is a quadratic. That is the saddest quadratic I have ever made. Woo! All right, now reflect this in the y-axis. Okay, I'm not saying you have to say this or draw this, but I'm reflecting over that. All right, reflect this in the y-axis. Well, I'll give you a few seconds, and you reflect it in the y-axis, and you can let me know when you're done, because I'm done. And you're going to say, what do you mean you're done? Well, think about it. Will not this point here at 1, negative 3 flip over to negative 1, negative 3? But then, this point at negative 1, negative 3 will flip over and become 1, 3. All right? I try and explain it like this to students. Imagine if I was flat. If I turn around and I was flat, has anything changed? No. All right? I'll still have the same shape. So reflect this thing in the y-axis. Done. How does the reflected graph look different than the original graph? It doesn't. It's the same graph. Describe the location of any invariant points. Now, we got to be very careful about this one. All right? This point does move and jump over here. This point does move and jump over there. So the only invariant point is what's on the mirror line. And I believe that it is going to be 0, negative 4. Now, why is this the invariant point? When you reflect over the y-axis, your x's get negatives. Well, negative 6 becomes positive 6. Positive 9 becomes negative 9. What happens to a 0 when you put a negative on it? Nothing. So here's the key. We are clearly dealing with this. We are dealing with the reflection over the the y-axis. I apologize. Meaning the negative goes on the x. Well, what's the only x that doesn't change when you put a negative on it? 0. So when we flipped over the x-axis on the previous question, x-intercepts were invariant. When we flipped over the y-axis, the y-intercepts are invariant. Which means, if I just go back one page for a second and I talk about this diploma question, the diploma loves to say, okay, I'm going to give you this original function. And then as a numerical response, they say, how many invariant points if we flip over the x-axis? How many invariant points? 1, 2. How many invariant points if we flip over the y-axis? 1. So they like it as a numerical response where the answer would be 21. All right, common numerical response diploma question. All right, determine the equation of the reflected graph to explain why the graph looks the way they do. Okay, now, do you agree we're putting a negative on the x? All right, up here, I'm about to change that x to negative x. Terribly sorry. I want you to think about this. This was the original equation, x squared minus 4. Okay, that was the original. Now, we are changing this x right there into negative x. All right. Now, the squared is still there, and the minus 4 is right here. Now, this is the equation of the transformed graph. We are putting a negative on the x's. What's about to happen when you square the negative? Oh, it becomes positive. Oh, we end up with this. Changing the x to a negative x has no influence because the square squares it back to positive. This is the reason the graph didn't change, because changing this x to a negative x doesn't do a thing because of the square. Now, if we had reflected over the x-axis, I'm not saying that this was the question, but if they had wanted us to reflect over the x-axis, wouldn't negative 4 have jumped up to positive 4? Wouldn't these fives jump down to negative 5? I realize that I'm jumping the gun and just having a little bit of fun here, and this graph would have looked like this. Oh, no, my bad. Oh, that's terrible, Mr. Chandler. Sorry, would have looked like, that's better, Mr. Chandler. Watch what you're doing. There it is. If we had reflected over the x-axis, we would have turned it upside down. Notice, reflect over the x-axis, x-intercepts are invariant. Had we reflected over the x-axis, that means put a negative on the entire function. Look back here one page. When you reflect in the x-axis, put a negative on the entire function. If I put a negative on the entire function, well, negative 4 becomes positive 4. Hello, y-intercept. Negative x squared. Does this negative get touched by the square? No. So that's why green is a reflection in the x-axis. All right. Now, we've got this. We've got an x plus 3 squared minus 2. All right, no problem. Now, just a quick, I'll just throw it right here just for some funsies. Do we agree that this is 3 left, 2 down? A little 1, 2, 3, 1, 2. This vertex is over here at negative 3, 2, and I'm just doing a quick, whoop, it looks something like that, more or less. Don't really care, but clearly starting in quadrant 3, opening up. Now, sketch and write the equation for negative f of x. This means put the negative on the y values. Will this thing not become, instead of negative 3, negative 2, won't it become negative 3, positive 2? 1, 2, 3, 1, 2. I think this guy now has a vertex here, and I think he's going to look something like that. And I'm assuming on your calculator you will be able to deal with that better. What does this mean for an equation? It means put a negative on the whole thing. Our new equation becomes negative x plus 3. There she is, all squared, plus 2. Because when you put a negative on this whole thing, the negative 2 becomes plus 2. We are still 3 left. 1, 2, 3 left. Up 2. Up 2. And if you remember from Math 20, a negative a value, oh, she opens down. I apologize, I didn't mean to put that right there. Thus, the original guy opened up, the new guy opens down. All right? Now, this says put a negative on the x. This is a reflection in the y-axis, meaning -3, -2 will become +3, -2. 1, 2, 3, 1, 2, boom, vertex right there. This guy will now look, oh, that was ugly, Mr. Chandler, but you get the point. This guy now flips over the y-axis, because when you put a negative on the x, then lo and behold, it is a reflection in the y-axis. Now, where would the invariant points occur? Whatever the y-intercept is. I realize I never asked about invariant points, but the invariant point would be the y-intercept. Now, how difficult is it to get a y-intercept? Not terribly. I mean, what's the definition of a y-intercept? When x is 0. 0 plus 3 is 3. Squared is 9. Minus 2 is 7. This guy is going to cross right here at 7 and cross right here at 7. So lo and behold, the invariant point would be 0, 7. This guy, whatever his x-intercepts were, the invariant points would be the x-intercepts. And he doesn't have nice x-intercepts because you're going to move the 2 over, square root 2, which is an irrational number. So now you've got like 1.4 and then negative 1.4, and then you have to subtract 3 from both. So, we're not talking about very nice numbers here. But that's where the invariant points would be on this guy. All right? Now, they want an equation? Fine. Put a negative in for that x. You see that x? I'm changing him to a negative. So he's simply going to become, let's just go with this. We got an equal to, I'm looking at a bracket, negative x. What do I got? Plus 3, got you, squared, minus 2. There is the equation for this particular transformation, because this x just got replaced with this negative x. All right, I think I'm on the last page here. Let's see what we got here. Am I on the last page? Yeah, I am. Look at that. All right, no problem. So we've got a graph whose f of x. And f of x is simply an absolute value. No problem. Now let's think about this. This is 4 to the left and 1 up. Okay, so I realize it never asked me to do it, but here's 1, 2, 3, 4, 1 up. I believe that his vertex is going to be right there. And this is an absolute value, so he's a V. Is he not? Not a problem. Now, it's reflected in the y-axis. Okay? So lo and behold, to reflect this thing in the y-axis would now put it over as 1, 2, 3, 4, right there. And I think it would look something like that. No problem. I have reflected red in the y-axis, and it would produce green. Fine. This produces the same result as translating the original function to the right by. Well, do you agree that yes, red got flipped over to make green? Well, couldn't I have also just literally picked red up? Let's see if I can do this. Pick red up and move him over. Actually, I'm not that bad. Wow, that's pretty impressive. Pretty proud of myself. So how could I have done that? Well, couldn't I have just moved him over 8 units to the right? So I believe that my answer here is simply going to be 8 units to the right. What a beautiful numerical response question, if you ask me. Because, right, positive, the answer is 8. Great numerical response question. All right, example. 5x plus 2, and then negative 5x plus 2 is a reflection of the, no problem, got it. Now, I know what the answer is, because I know what it means to put a negative on the x. Because that's what this is asking. It's asking, put a negative on the x. Notice the 2 didn't change. So this is a negative on the x. Wait a second, I think it's right here. But I'm going to prove something to you. Let's come back to it. Okay, fine. Grade 10, 5x plus 2. Grade 10. I believe that we got 1, 2. This guy is going to look something like this, and he's going to go right through there because we got a slope of 5 with a y-intercept of 2. All of a sudden, grade 10, the y-intercept is still 2. Gotcha. And what are we going to do? We got a slope of negative 5. So this guy now comes like, I'm sorry. See if I can move him down slightly. I missed my y-intercept. For all my drama students, I missed my mark. There it is. All right. So now, we just reflected. Did we just reflect over the x-axis or the y-axis? Well, to me, the invariant point is the y-axis. To reflect over the y-axis gives invariant points of the y-intercept. Therefore, I think this is a reflection in the y-axis. All right? So to me, I believe the answer is B. Now, the interesting question becomes, did we reflect in both? All right? Did we reflect in both the x-axis and the y-axis? I don't think we reflected in the x-axis. And the reason I say that is because positive 2 stayed as positive 2. I didn't jump down here to negative 2. I ain't going through this point here. So I can't say that I've reflected in the x-axis. So I'm liking the answer of B. All right, what do we got here? We got some function is the absolute value of x plus 3. Okay, no problem. We got a nice 1, 2, 3. I believe that this is an absolute value function, so I think she's just going to be a nice V shape. There it is. And we are reflecting in the y-axis. Meaning, right side, I want you to jump over to the left side. Left side, I want you to jump over to the right side. Write the transformed equation. Will anyone else notice that she ain't changing? Well, how come? To reflect in the y-axis, let's go back a couple pages. To reflect in the y-axis means the x's become negative. Okie dokie. So lo and behold, you see this x? It's about to become negative x. Okay. So in other words, it's now absolute of negative x plus 3. Wait a second. I don't care what you do to this x. You make them positive, you make them negative. What's an absolute value always going to do to them? Make them positive. This x will never change. He can be positive, he can be negative, but the absolute value is always going to make him positive. Hence, reflecting this guy in the y-axis did diddly squat. Write the transformed equation? Gotcha, right there. And I should write f of x. There she is. Now, do I think the diploma might do this? Sure they could. Do I think the diploma might say, well, wait a second, the absolute of a negative is just going to be positive, so is it possible for the diploma to actually give an answer that is unchanged? Sure they could. I don't have a problem with either one of these. They are both correct. Alrighty, so here we go. A reflection in the x-axis. Is this up, down, or left, right? Well, to reflect in the x-axis means if you were here, then now you are here. Agreed? If you were here, then now you are, let's see if I can find a different color, there's yellow, then now you are here. Actually, I'm trying to make those horizontal lines. Let's do that again. If you were here, then now you are here. Got it. So to me, this is an up-down issue. What's the mapping notation? Well, you are only going to influence the y's. So the x stays the same, the y gets a negative on it. If you were positive, now you're negative. If you were negative, a double negative makes you positive. What is the new equation? Well, therefore, it is simply going to be this. We got y equals f of negative x. All right, because we are reflecting in the x. Whoa, Mr. Chandler, what are you doing? Oh my goodness, that is embarrassing. Sorry about that, students. I was doing the wrong one there. What happens when we reflect in the x-axis? So terribly sorry. The x stays like that. I did this correct. I just put the negative in the wrong spot. I'll even make it red so you can really see it. The negative goes on the entire function. I apologize. Sorry about that. What that means is that the y's change. Your x doesn't, your y does. What is the location of any invariant points? Well, go and put a negative on a y value of 0. Therefore, nothing changes. Your location of invariant points are going to be your x-intercepts. 0, comma. Oh, my goodness, Mr. Chandler. Can you tell that it is clearly bedtime? I gotta just give up and go to bed. Take that back. Try that again. X-intercepts. X, comma, 0. That's better. Woo! Seriously, I'm going to bed after this. Alrighty, what do we got? We are now going to reflect in the y-axis. Not a problem. To reflect in the y-axis simply means that if you were here, you are now going to move to here. This is clearly a left-right issue. It is the x that changes, meaning negative x, comma, y. I apologize, kind of hard to see that negative, so what I'm going to do for you is I'm just going to put a negative right here so you can really see it there. It is the x that gets a negative. Well, what happens then? We've got f of negative x. There she is. That's better. And then where are the invariant points? On the y-intercept, who are going to be 0, comma, y. Sorry about that, students. I made some blunders in this last section here, but with any luck, I have cleared them up. Alrighty, so all we're talking about today is reflecting over the x-axis, up, down, reflecting over the y-axis, which is a left-right. We got our assignment right here. You need anything, you know where to find me. Take care. Thanks.